Okay. I think everything works fine. I hope you can also see us on YouTube. Okay, so welcome. Good afternoon, everyone. Let's begin our next Tuesday seminar at the Astronomical Observatory of the University of Warsaw. Today's speaker is Małgorzata Curyło from our observatory. She's the third year PhD student under the supervision of Professor Tomasz Bulik, and she's going to tell us about gravitational wave search with pulsar timing arrays. Małgorzata, please.
Thank you. Hello, everyone. I'm really happy that I can make this talk for you today. So I have divided the presentation into 3 parts. So I will start with an introduction on how pulsar timing arrays actually work. Then I'd like to give you some short summary on some recent, most important studies that have been published recently by the collaborations. And as the last part, I will show you my own preliminary results on the work that I do based on the data sets gathered with this 64-meter telescope in Parkes, Australia. So I'd like to start with a plot that I think everybody is familiar with, but it will place my presentation in some context following the presentations that you've heard for the past couple of weeks. So here is the gravitational wave spectrum, and on the starting from the right-hand side, you can see the highest frequency range of about several hundred hertz that are probed by ground-based detectors like LIGO and Virgo. And as we move to the left side, going down with frequencies, we will also be moving in towards the longer time periods or larger orbital separations, or in other words, more massive objects that we could try to detect. Roughly speaking, if we want to probe the lowest frequency, the lower frequency we want to probe, we will need our detector to have longer arms. So if we start with ground-based detectors, we have about 4 kilometers long arms. Then LISA in space will have about 2.5 million kilometers arms. But it will be quite difficult to build a detector that would be even bigger. So our idea was to use some of the natural resources that we can find in the universe, and these would be pulsars. The very similar plot, but here you can see the characteristic strain and the comparison between the strain sensitivity of detectors, ground-based detectors, LISA detector, and here is the PTA pulsar timing array detector, along with the future SKA that we still have to wait for. Important to note here is the shape of the gravitational stochastic background that we will try to detect with pulsar timing arrays. It is given by a very simple equation. Here is the amplitude of the stochastic background and a spectral index, which will be which is predicted to be minus 2/3. Here on this cartoon, you can see the basic idea standing behind pulsar timing and how to detect gravitational waves with it. So if we consider a gravitational wave coming, propagating somewhere between the Earth and the pulsar, we would expect the space-time to be squeezed and stretched, and that would change the observed frequency of the pulse we observe from the pulsar. The frequency will be Doppler shifted. As the gravitational wavelength is much shorter than the distance between the pulsar and the Earth, the wave will act at a different time at Earth and at the pulsar, and this is so-called the Earth term and the pulsar term. So in other words, when we want to measure the gravitational wave, if the gravitational wave will pass between the Earth and the pulsar, we will see that the times of arrival of the pulses, the so-called TOAs, will come a little bit earlier or a little bit later than expected, than if there was no gravitational wave in between us. So because of this this difference between the Earth term and the pulsar term, the timing perturbation that we will see in our measurements will be just the difference between the strain seen at the Earth term and at the pulsar term. It is important to note here that the signal that we measure at so-called Earth term will be correlated between different pulsars, because the gravitational wave will influence the clocks and our measurements here, and this will affect all of the pulsars that we observe. We will see no correlation for the pulsars, because if the gravitational wave passes, it will reach different pulsars from the array at a different time. So in fact, the pulsar term will actually act as an additional source of noise, and hunting for gravitational waves with pulsar timing arrays, we will need to search for this correlated signals. And I will talk about this a little bit more in the next slides. Here you can see how we actually make this kind of measurements. So we observe a millisecond pulsar. Millisecond because their periods are really incredibly stable. So we are measuring the time of the arrival of the pulse, and then we compare it with a theoretical model that we are preparing based on all of the processes that we may think that might affect the behavior of the pulsar. These are, of course, the spin period and the spin derivative, the position of the pulsar, the binary parameters, because actually almost all of the millisecond pulsars are in binary systems. And so if we have this model and we compare it with TOA, we can subtract one from another, and then we get a residual. And this shift will actually tell us that something might have happened on the way between the pulsar and us. It might be a gravitational wave, but also it might be noise, which is more probable. Or we can also make some errors in our modeling. Basically, if we make a very good model and we extract all of the noise that could interfere with us, we expect the residuals to oscillate around 0, and basically that would be just the white noise. Any errors in the model or noise would change the shape of the residuals. So now the question is how these residuals will look like if we saw a real gravitational wave. And here on this plot, you can see the 4 basic kinds of sources that we can see. On the A plot, you can see the continuous waves generated by a single spiraling binary of supermassive black holes. On the B plot, you can see the stochastic background that will be just the cosmological population of all of these supermassive black hole binary population. Here on the bottom, you can see the burst and burst with memory. The burst will be just one finite rapid event. For example, a close encounter of 2 supermassive black holes on a very highly eccentric in a highly eccentric binary, or even an unbound binary, while burst with memory would make a more permanent imprint in the space-time. And these sources, for example, this might be a final stage of in-spiral or the merger of supermassive black holes. There are 3 three very important things that we can extract here from these plots. First of all, it's obvious that as gravitational waves, we are probing a very low frequency. We are probing several year of time scales. So it is important that we make decade-long observing campaigns. And this is actually what is happening because our current data sets from PDA have around 15-20 years. The second thing is that the gravitational wave amplitude in the residuals will be of order of several tenths of nanoseconds. So we need really incredible precision in pulsar timing. Here on this plot, you can see that the error in a measurement of a single TOA, single measurement, is of order of 1 nanosecond, which is just too perfect. Our current sensitivity is of order of 3 orders of magnitude lower. So there's a lot of to do for us in this manner. The third thing and the most important thing is that the waveform, the form of the signal we detect will depend on the relative position between the source and the pulsar. And this is shown here with 3 colors. You can see signal generated by the same source, but seen in 3 different pulsars. As I said a while ago, if we want to confirm a detection, we need to see this correlated signal between different pulsars. And this correlation is given by a so-called Hellings and Downs curve. The shape of this curve is comes from our knowledge about gravity, polarization of the gravitational wave. But it is important to know that the correlation between the pulsars that we will see will depend only between the angles of the pulsars. So there cannot be any. So we cannot state that we detected a gravitational wave only by observing just one pulsar. We have to see this specific kind of correlation between the pulsars, this spatial correlation. Here I'd like to show you how do we work. We actually have right now 3 separate collaborations that work that get their own data, and these are in Europe, EPTA, in North America, Nanograph, and PPTA Parks Australia, where also I work. And we also work together as International Pulsar Timing Array, and sometimes we gather all of our data sets that are analyzed separately to make one big data set that would be most sensitive. So here I'm moving to the second part of my presentation. This is just a short list of most important research done recently in PDA. First, you have the latest data sets, couple decades long data sets that have all of the timing models and timing residuals for all of the pulsars we currently observe. And along with these data sets, we have searches for stochastic gravitational wave background. We have searches for individual supermassive black hole binaries, for bursts in gravitational waves, and also a lot of other searches for some more exotic sources like cosmic strings or dark matter. In the next few slides, I'd like to show you the most important results on searches for isotropic stochastic background and continuous waves, and I will leave all of the other research for interested people here listed in the in these papers. So first, I'm going to start with continuous gravitational wave upper limits. This search was based on 11-year data set. On the left side, you can see the gravitational wave strain upper limit in terms of frequency, and besides the upper limit for an 11-year data set. You can also see the 5 and 9-year data sets and compare the sensitivities and how much they increase with the increase in our data sets. So the calculated continuous gravitational wave upper limit because we didn't detect any gravitational waves based on this data set, was placed to be less than 7.3 times 10 to minus 15 at 8 nanohertz frequency, which corresponds to the most sensitive region. When we transform this, translate this into the horizon and the distance to which we are sensitive, it would be around 120 megaparsecs. The conclusion from this research is that with the analysis did not find any supermassive black holes emitting gravitational waves in the PDA frequency range within the Virgo cluster. It might seem quite not a quite depressing result maybe, but actually it is consistent with our theoretical predictions, because only 34 of about 75,000 simulated realizations of the local universe contain a detectable source. So this is completely consistent with each other, although we will still need to improve our sensitivities in order to detect continuous gravitational waves. That research was based on 11-year data set, but now this year we have two major releases from Nanograph of 12.5 years and Park's 14 years of data. On the left, you can see the Nanograph data. Each point here shows the single observation of each pulsar, while on the right side you can see the Park's data and all of the timing residuals that we obtained by our analysis. Here, the RMS of the observations is similar in Nanograph in Park's. For majority of pulsars, we reach sub-microsecond goodness of our measurements, which is promising, but still we need more improvements. Alongside with the 12.5-year data set from Nanograph, there was this paper released recently on search for isotropic stochastic gravitational wave background, which made quite a lot of noise in the community, because the paper states that we have detected some kind of a common spectrum red process in many observed pulsars. The red process will be the long wavelength process, which would be gravitational waves would seem like a red process in our data. And actually, after taking closer look to the residuals in terms of the frequency, we can see that the spectrum, the amplitude, and the spectral index of this red process is actually consistent with what we would expect from a characteristic spectrum to gravitational waves. The problem is the other exciting thing was that we observed it in many pulsars. So maybe this process is actually correlated with each other. First, we checked that the signal is not sensitive to the choice of the solar system, which was a problem with previous data sets, and we clearly see that both ephemeris models state a certain amplitude of this common spectrum process. But unfortunately, there is no clear evidence on any quadrupolar spatial correlations between the pulsars, which would be necessary to claim the detection. On this plot, you can see the comparison between just the common red process without any statement of the spatial correlations between the pulsars, and the probability distribution function for a hypothetical gravitational wave background, and there is no clear evidence for that. To further search the data and see what is actually happening, what is this source here seen in the spectrum, the authors also checked other correlations that might indicate other noise processes that would look similar to the gravitational waves, and these correlations are moderately disfavored. Here, the bias factors have values that disfavor these correlations. Continuing the analysis and searching for the reason for the common red process, we did a so-called dropout analysis, where this dropout factor would tell us how much a given pulsar is contributing to the common spectrum process. And you can see that the dozen of pulsars definitely say that definitely contribute to the spectrum, but there are a few that say that no, they didn't detect anything particular. Right now, we are analyzing the data sets from parks in order to compare them and try to look for the reason for such correlations. The data set from parks is not yet published. Preliminary results are pretty consistent with each other, but what's interesting is that analyzing different sources of noise in pulsar timing data from the newest 14-year data set from parks, we found some interesting correlation, and this is showed here in this picture. You can see the spectral index of the noise processes and the amplitude of the noise processes. Specifically here, you can see in red the spin process, and with the dashed line, you can see the spectral index characteristic to gravitational waves. And it turns out that there are few pulsars that are clustered here around the spectral index of gravitational waves, and this actually comes from their spin noise. And it turns out that these are exactly the same pulsars that are showed here that contribute the most to the red process discovered in nanograph data. As nanograph observes in the northern hemisphere, parks in the southern, we don't have full compatibility, but still we have these few pulsars that state the same thing. It is important that these few pulsars are one of the best timed pulsars, and it was already known that the longer we time the pulsars, the spin noise in these pulsars becomes more and more significant. So maybe this is some hint of what might be actually the reason of the detected common spectrum process in the nanograph data. But right now we cannot make any specific conclusions on that. We have to wait for the specific analysis of the parks data. And then when we combine this all data within the International Pulsar Timing Array, we might be able to actually say what is the actual reason for this kind of spectrum. Nevertheless, these results are really exciting because we are currently we're reaching the limits of the gravitational wave background that we would expect, and we are actually seeing some structures in the data. And this is the third part of my presentation, where I like to tell you something about my own work in Parkes Pulsar Timing Array. We are currently trying to make the timing analysis more and more sensitive to gravitational waves. And here you can see on this plot, in a black line, you can see the sensitivity of the nanograph 12.5-year data set. And here we can see what we can do to make the sensitivity better. First of all, we can increase the number of pulsars in the array. And we can also increase the cadence of the observations. That will make us more sensitive to the higher frequencies in the band. But what we can also do is to upgrade our telescopes, our receivers, because the uncertainties correlated with the telescopes would directly influence the precision of single TOA measurements, and making them better, we can go down with the RMS and increase our sensitivity. As you can see from the radiometer equation here, the uncertainty coming from the receiver we are using is inversely proportional to the effective aperture of the telescope. So the bigger telescope, of course, the more sensitive we are, but it's also inversely proportional to the square root of the bandwidth that we are observing it. And as we cannot make our telescopes bigger and bigger and bigger, and we cannot also extend the time of our observations because there are many people that want some time on our telescopes, the extending the bandwidth is actually one of the major directions in which all of the PDAs want to go now. This is what actually has already happened in parks, where we installed and commissioned so-called UWL, ultra-wideband receiver, that is covering the frequency from 700 megahertz up to 4 gigahertz. And in the future, we will extend it up to even 24 gigahertz. In comparison, the current nanograph receivers have frequency bandwidth of about 500, 600 megahertz. So this is actually a very, very big step in increasing our sensitivity. Since 2018, we are observing 40 millisecond pulsars with a standard 2-3 weeks cadence, which always been the same for all of the data sets. But unfortunately, increasing the bandwidth comes along with a lot of problems. And one of them is the profile evolution, which is substantial for many millisecond pulsars. Here you can see how it looks like for two different pulsars. As we go up with the frequency, the mean pulse is changing. This is affecting our TOA measurements because we are trying to make a measurement based on such a mean profile, and as it's changing so much with the frequency, it's really hard to make a precise measurement. We don't know at which frequency we would have to make this measurement. There is actually no direct solution in traditional timing methods right now for this problem. The indirect solution will be to divide the whole band into subbands, derive a mean profile for each subband, and measure the TOA for each subband. But this is another problem because this would substantially increase the number of TOAs. And when we increased our bands and increase the number of pulsars and years of observations, it will be just computationally too expensive to analyze this kind of data. The other problem is that we have a dispersion measure, which is the effect that the times of arrival of pulses on different frequencies are different. So pulses on highest frequencies are coming to our detectors earlier than those coming from the lowest frequencies. So this is another thing that we have to take into account when we are observing in a very, very large bandwidth. This is how we are trying to deal with these problems in parks right now. This is the first part of my work. We try to apply a new approach of analyzing the data, and instead of generating a sub-banded TOAs for every sub-band of our wideband that is averaged in frequency, we are generating a 2D, two-dimensional template that is maintaining the phase and frequency resolution. What is also important, simultaneously we measure the TOA and dispersion measure once per whole band. So we don't have to make any guesses about how the dispersion measure changes with the band. We also don't measure TOAs differently using different narrowband profiles. We all do it very consistently, and that's why this technique may give us more precise measurements. This is just a summary of how it works. First, we make an average noise-free portrait, maintaining the frequency and phase resolution. We decompose this into basic functions, so-called eigenprofiles, via principal component analysis. These eigenprofiles, they are just tracing, here is the mean profile, and these eigenprofiles are tracing how the profile is changing with the frequency. Then we just feed a spline function to the profiles that are projected onto eigenprofiles, and every such projection is here with the purple square circle, and the spline function is in green, and this spline function is telling us how the profile is evolving with frequency, and information from parameters from this function enables us to make a TOA measurement that takes into account the profile evolution. And these are these results. We started with two pulsars that are well timed. J1909 is one of the best timed pulsars. It shows very little profile evolution. That's why it was good to start with this one. Here you can see the average portrait of 10 highest SNR observations, and there is this model that is made upon these observations, some residuals and the goodness of the fit. And here you can see the mean profile, which is really simple, which is also described only by one eigenprofile. The more the pulsar is evolving with frequency, or the more noisy is its data, we would see more eigenprofiles, because we would need more data to express the profile evolution. After measuring the TOAs, we compared it to a timing model. We fit it into a timing model and gained these standard residuals, and also the DM measurements for every single observation that we've done in these 2 years of gathering the data. We gained RMS of about 100 nanoseconds. We did the same analysis for J0437, which is the brightest pulsar in the southern hemisphere. The difference is that you can see here in the middle plot that this pulsar exhibits a very severe profile evolution with frequency. That's why you can see that we have more eigenprofiles that were needed to explain its evolution. After some basic timing, we can see that we have some problems here. Single measurement uncertainties are much smaller than the general scatter in the data, and we compared this kind of scatter with the data already available in the literature, and we can see that this pulsar is severely affected by so-called jitter noise that is coming from the variability in the single pulses of the pulsar. And for a 30-minute observation, that we have for a single measurement, the jitter noise would be about 80 nanoseconds, and this actually corresponds to what we see in our data. After applying noise analysis, after excluding other noise sources, we obtain a really nice residuals also for this one pulsar with RMS also around 100 nanoseconds. Here on this plot, you can see the summary for the wideband timing. In the table, you can see two of the pulsars we have observed with our ultra-wideband receiver. These are the data from Park's data release from this year. This one is from Nanograph, which wasn't observing this one pulsar, and from the whole IPDA from last year. As you can see, for the first pulsar, we have a just slightly better sensitivity. It's not surprising because this pulsar is really a simple one, doesn't have much profile evolution, is not very noisy. So the standard techniques of analyzing its data show good results. So we don't see much different, but still we have increased in sensitivity. The remarkable results are seen for J0437, where we have increased our sensitivity substantially in comparison to the similar data from Park's, and it's just calculated over 2 years of observations, while Park's second data release has 14 years of data. So these results look really promising, and we will apply them for many other pulsars in the array. To summarize basic concepts of wideband timing, we can see the significant reduction of data products. Here you can see the average number of timing TOA measurements from Park's data reduced to 2 years, and TOA number measured for UWL with the new analysis techniques. This will enable us analysis of much larger sets in the future. Also, Nanograph has analyzed its 12.5 data sets with narrowband analysis, this old methods of timing, and with this kind of wideband timing, and the results are consistent with each other. We can see the improvement for pulsars with a substantial profile evolution, like just for these two we've seen. We can see also the recovery of low SNR profiles, which would have to be excluded otherwise. And now we also can use the low SNR profiles. And was also very important that wideband data sets and new algorithm lower the number of timing parameters, because we don't have to add additional parameters to fit for the dispersion measure and different TOAs for different subbands, because we do this just once for the whole data set. And this is my summary plot. So essentially, PDA will provide a complementary view to gravitational wave detections with ground-based and spaced detectors. For some sources, for example, if we can see their evolution from the PDA band, where the orbital periods are of orders of decades, to LISA band. So that would be a marvelous thing to see, to perform multi-band gravitational wave observations in the future. Our current sensitivities also already reach the upper limits on predicted gravitational wave background, and already disfavor some of the more optimistic models. It will in the future enable us probing galaxy formation and galaxy black hole dynamics, put estimates on galaxy merger rates, which are very poorly constrained right now. And also we'll test the theory of gravity in nanohertz region. What is really exciting to say to the end, we expect the first detection in the next few years. Here you can see the predicted SNR of the signal in the 15-year data set from nanograph, which is already being analyzed, when we inject the same signal that was detected in the current data set. So if we assume that this signal was really astrophysical, in the next data set, we would see the detection with SNR of the order of 7, which is really, really exciting. On the left, on the right plot, you can see estimated sensitivity to IPTA by 2030s. So this is exactly when LISA is expected to launch. So these are going to be really exciting times in pulsar timing and in gravitational waves. Thank you.
Okay, thank you very much for this very interesting talk. We have time for some questions. If you want to ask a question, please raise your hand, the blue hand. Yes, like that. So I see first question came from Milena, please.
Hello, hi Gosia, thank you for the talk. I was just wondering, as just to ask you about the very general thing. There is this big Chinese radio telescope, it's called FAST, and we are in a stage of building of SKA, and this two facilities just before LISA and other more sophisticated stuff. How will they influence the gravitational wave search with PTA?
They will be actually very important, and they. I had this here. I showed you the radio equation where the uncertainty will scale with the effective aperture of our telescopes. So if we extend it up to 500 kilometers, like with FAST, it will substantially increase the sensitivity. SKA will make it even better because this will be an array of telescopes with kilometers of aperture. So on the second plot here, I showed the predicted gravitational waves strain sensitivity for SKA. As you can see, it will go really down into the stochastic background as well to the supermassive black holes. So with these kind of telescopes that you're talking about, we expect to detect gravitational waves, and we will not have to struggle this much as we do with PTA, where we care so much for every single noise in the data.
Thank you.
Okay, next is Tomek, please.
Thanks again. So my question is about the pulsar profiles. I understand that these pulsars are in binaries, and you may expect that there might be precession in these of the neutron stars that are emitting, and precession may lead to change of the profiles with time. So is this something that you already worry about, or do you see it in some pulsars, or this is yet another thing that may be important, but at this moment doesn't play a role?
This is an important thing, and it does play a role now because yes, all of the pulsars that we observe are in binary systems. That so making models, precise models of timing for those pulsars, we have to take into account processes like precession. This generating timing models is actually one of the most difficult thing in timing, it generates a lot of noise, and it generates a lot of problems with the residuals. I haven't been working on this, but this is the precession is one of the things that is carried by the precision in building a model.
Okay, any more questions? I can ask one, how well can you localize the gravitational wave source if you have multiple pulsars on the sky? Is it at all possible to say the gravitational wave source came from this direction, and how well can you estimate the direction of the source?
I think I'm not sure how good would be the estimation, but it will be really much better than in case of ground-based detectors, because we will detect the gravitational waves with the whole array of pulsars that are around Earth in every direction. So this will and the signal will depend on the angle between the gravitational wave and a given pulsar. So it will, I think it will enable us to localize them with a quite good accuracy.
Mm-hmm. And also you showed on your plots that if you go not in the 2030s, but maybe later, if you go deeper in your sensitivity curve, you written then there that you can detect PBHs. Is that right? Do you mean binary primordial black holes, or what?
You mean this one?
Yeah, I mean this one.
Yeah, primordial black holes. Yeah.
Are they binary primordial black holes you can detect, or single? And what would be the effect? How would you detect them?
This is a good question, but I don't have an answer for it right now. I wasn't looking into
maybe I'll comment that the properties of primordial black holes are a domain of theory, and the existence of binaries among them depends very strongly on the particular theoretician that you talk to. So there are people who claim to explain all the LIGO, Virgo black holes as PBHs.
Right.
And I think we even had one talk at the observatory last year, but making them in binaries, I think is quite difficult, because they would have to form at a particular moment in the universe, and each of them would be formed under the horizon at the time. So then their velocities are uncorrelated, so you have to invoke mechanisms like in dense stellar clusters to make binaries later, and otherwise it's quite difficult.
Okay, thank you. Any more questions? We still have a couple more minutes. I don't see questions here. I don't think I see questions on YouTube neither. So thank you, Małgorzata, for this talk. Thank you all for joining. We had almost 40 people. That's great. And this was the last talk in the series about gravitational waves. And with the next talk, we move on to a different topic, which will be astronomy and astrophysics from space. Okay, thank you all, and goodbye.
Bye. Thank you.
Thanks. Bye.